Hello and good morning. This is a short video that is going to serve as a preamble to our discussion on the regional geology of Nigeria and in the future regional geology of Africa. I like to give this context because it helps that, especially when you look at the regional geology of a large area, when you're going into regional geology, it is useful to understand certain concepts because in discussing the regional geology of a region, especially its tectonic evolution, we're going to use concepts that are based on the theory of plate tectonics. Because when we look at the Earth on the regional scale, the theory of plate tectonics comes into play. So it is useful to understand, for example, ages, the geologic time scale in detail. It's useful to be used to the geologic time scale in detail. And it's useful to understand certain terminologies that have to do with regions, especially tectonic regions. So we're going to look at some of the most important concepts or definitions of things, of words that will be used a lot in our explanation so that as we're going through the regional geology of different parts of Nigeria and in the future of Africa, we do not get confused by certain terms as we hear them. So, first things first, we have to be very, very familiar with the geologic timescale. The geologic timescale is available online if you just search for the International Chronostratigraphic Chart. It's available and it's constantly updated by the International Commission on Stratigraphy. It's constantly updated. So it's good to go download it, have it, and refer to it constantly until you get used to the names. Because most times it is not the you don't it's not mentioned that so and so event happened so and so million or billion years ago, as the case may be. What is mentioned is so and so event happened in the Proterozoic, in the Neoproterozoic, in the Santonian, in the Coniacian, in the Oligo-Miocene, in the Neogene. These are the kind of words that I usually use, and it's good that we have a grasp of them or we have an understanding of them, or at least we know where to refer to when we hear those words. So when we hear Neoproterozoic, we can always go look at the chart and see, the Neoproterozoic is from a billion years to 514 million years thereabouts. And then it gives you a kind of understanding of the story as it's being told. So in our study, especially of the geology of Nigeria and the geology of Africa, for the geology of Africa, Africa basically has rocks of all ages, if we're putting it like that, from the Archean all the way to the recent. For Nigeria, you'll be more concerned about the Archean and Proterozoic into the early Cambrian and the Cretaceous down to the recent. With Nigerian sedimentary basins, you are dealing with rocks that are from, at oldest, Barremian in the lower Cretaceous, all the way down to recent. So these are things that you have to get conversant with. For the Cretaceous, you have to get conversant with the stages, the different stages. So from the Barremian to the Aptian to the Albian to the Cenomanian, all the way down to the Maastrichtian. You have to get used to it because the rocks in the Nigerian sedimentary basin, specifically the Benue Trough, are of those ages. And when we are mentioning different formations, it is what is usually mentioned are those ages and are those names. So you hear this unit is Cenomanian, Turonian, etc. Okay, so a few things. When we look at regional geologic features, the regional geologic features worldwide are studied within the context of plate tectonics. Because plate tectonics is, we can say, the model for the Earth's lithosphere, the global model for the Earth's lithosphere. And what is this model? The Earth's lithosphere, according to to the plate tectonic model, the Earth's lithosphere is seen as made up of plates. So we can understand plates as the crust, the Earth's lithosphere, which is the crust and the uppermost part of the mantle, is broken up into plates, into pieces, into plates, interlocking to the large extent pieces called plates. And these plates move relative to each other. They move relative to each other. And it is in that movement that the forces that are driving those movements and the interactions as a result of those movements that yield tectonics, the tectonic features of the earth. And these tectonic features are the sum of the physical deformational processes that yield the regional scale geologic features. So any discussion about regional scale geologic features are discussions within the context of the plate tectonic setting. And the plate tectonic setting is broadly divided into whether you're dealing with a region where plates are moving towards each other, which is what you call converging, or moving away from each other, which you call diverging, or moving side by side, which you call transform. So these regions where plates are interacting in these three fundamental ways determine the different tectonic styles. And there are many subheadings under these three. So, for example, in places where the plates are coming together, you have situations where it's oceanic plate underneath oceanic plate or oceanic plate underneath continental plate where you have subduction. And then you have continental plates coming together where you have collision or what you will call your orogenic belt. Then you have rifting, you have range tectonics, and you have different areas. So every region, or if you're looking at the regional geology of an area, you're looking at it in the context of, first of all, what is the current tectonic setting? And also, over time, if you're looking at the tectonic evolution, over time, what has been the different tectonic settings that the rocks in that region have been in over geologic time. And that determines the assemblages, that determines the geologic structures, especially at the outcrop scale all the way all the way up to the regional scale, to the mega scale. It's determined by plate tectonics over geologic time. Okay. Now, closely linked to these are two ideas about how the Earth's plates and the Earth's crust has behaved throughout geologic time. The first one is the concept of, or the idea of the Wilson cycle. And the Wilson cycle basically describes a process that takes several 100 million years, where you begin from the opening by rifting of a continent, the creation of an ocean basin, and then the subsequent closing of that ocean basin by subduction. It's cyclical. It's cyclical. So most times when you look at the rock record in many different regions, you see that process has taken place, sometimes several times. So you go from a period where you have ocean basin creation and sedimentary deposition to subduction, collision, and deformation of those sediments during orogenic events. So that's the Wilson cycle. And closely related to Wilson cycle is what is known as the supercontinent cycle. And one can say the supercontinent cycle is basically what is at play on the global scale that is seen on the more or on the less global scale, on the regional or the semi-regional scale that is described by the Wilson cycle. So the supercontinent cycle is basically that it is believed, or let's not say believed, but most of the evidence point to the fact that you have cycles where you have continental breakup and then the continents separate into different continental masses, and then one way or the other they come together to form a supercontinent, and then that supercontinent is broken again into several continents, and then the process repeats itself over 300 to 500 million years. The most recent supercontinent was Pangaea, which formed 300 million years ago and began to break up 100 million years later in the Mesozoic to what we have now. There have been other supercontinents in the past in geologic time. And it is believed that the way the continents are moving, we're going to have another supercontinent in the next 200 to 250 million years. So it's a process that takes place. And the process of a continent separating, a supercontinent breaking into smaller bits, and then those bits moving around and then coming back together, it's basically that process of the Wilson cycle. Because when the supercontinent is breaking away, it's breaking away by rifting and the creation of new ocean basins. And then those ocean basins will close by subduction and collision to lead to another supercontinent. Now, this is the Wilson cycle, and it's good we go over this very, very quickly. And it's a video that you can always come back to. You can always come back to this video. So the Wilson cycle begins in stage A with a stable continental craton. It begins with a stable continental craton in stage A. And then you now have a period of rifting. And it's believed that this rifting starts from the creation of mantle plumes, and those mantle plumes push the lithosphere up, and then it begins to tear it apart. And it tears apart by forming what are known as rifts, rift systems, because rift systems are basically made up of normal fault systems with a lot of volcanism taking place as the crust is torn apart and extends, as the crust extends. So these normal fault systems with their graben structures, their horse structures, also form regions for sedimentation. And the sediments are usually immature sediments because it's basically the upthrown fault blocks that are broken down, and then they form alluvial fan deposits, which are usually conglomeratic. But over time, they become more lacustrine before you get to stage C, where the stretching becomes so much that you begin to have new ocean basin formation, which is what is known as the initiation of seafloor spreading. And once seafloor spreading initiates, you now have two continents. Your initial single continent is broken into two. And those two continents have margins. The margins where the continent passes into oceanic crust, and those margins are called passive margins. Now, what usually happens is that as the continents move away from the mid-oceanic ridge and the source of heat that is creating the mid-oceanic ridge, they move away from that source of heat and they begin to cool, and then they begin to sink. And in that sinking, they create accommodation space where sediments eroded from both continents are deposited. So at the margins of these continents that form from newly forming ocean, moving away from the mid-oceanic ridge, you have what is known as a passive continental margin, which can accumulate thick amounts of near-shore to marine sediments on what is usually called the continental shelf. As time passes in stage D, you have a fully wide ocean basin with its continental shelves on both sides. At some point, and it's something that we don't really know yet when it happens, you have what is known as island arc development begins to form. You begin to have subduction. So that oceanic crust becomes so cold that it begins to subduct. Typically, you have a volcanic island arc when you have ocean subduction. That is when one oceanic crust is being subducted under another oceanic crust. Now, just above that subduction zone, or just close to that subduction zone, obviously you have a trench, and the trench has deposits. You also have an island arc, which is made up of volcanism, which comes from partial melting of the rocks just above the subducting plates. And these form volcanic islands with so many things. There's deposition taking place because the volcanic island is also being eroded by rain and water, but the sediments are immature. The sandstones are immature because these are sandstones that come from mainly intermediate to mafic lavas, and then they don't really go very fast, so they are mineralogically immature. Over time, your volcanic island, because if you go back, what subduction does is that it's bringing the continents together. The first thing that begins to happen is that as subduction is taking place, your island arc begins to move towards your continent. When your island arc gets to the continent, it cannot be subducted because it's not as dense as the pure oceanic crust. It's less mafic, it's less dense, and then it cannot be subducted, and it collides into the continental crust. And in that collision, all your passive margin sediments are crumpled up into a mountain belt. They are crumpled up into a mountain belt. So there's a lot of compressional, or there's a lot of contractional deformation and metamorphism, as well as magmatism also. So you have your thrust faults and folds. And then also, one interesting thing, and this is something that we'll see a lot, especially when we look at the regional geology of Africa, is that Inland of your mountain belt, if we're looking at stage F now, inland of your mountain belt, you have a region where, because your mountain belt leads to crustal thickening, the crust thickens. You know, when something is floating on another thing, if the thing is thick, it tends to sink, it tends to press down. If it's thick and heavy, it tends to press down. So because the cross is thicker, it presses down, and then there's a region called a foreland basin close to your mountain belt, which is a depression that is as a result of the mountain belt pressing the lithosphere down. And that foreland basin obviously is a region of deposition because it's space that it has been created. And then the erosion from your mountain belt that has formed falls into that foreland basin, and then you have the foreland basin deposit. And the thing about the foreland basins is that the part of the foreland basin closest to the mountain belt, with time, as collision continues, the deposits of that foreland basin are joined into the deformation of the mountain belt. And that's what begins to happen. So over time, you now have a situation where your subduction zone now also gets to your western continent, the other continent that had its own passive margin, and then that now begins to move by subduction towards your already the continent on the other side, and then they collide, and then you have a continent-continent collision of two continents, and then you have a huge mountain belt in the middle, also with its foreland basin and everything. So you have a huge mountain belt in the middle. And in these things, you have what is known as the foreland and the hinterland. The hinterland is your main mountain belt, where you have your main orogenic belt. And then the foreland basin, the foreland is within the continent, where you have your foreland basin, and then you just have the parts of the continent that have not been affected. And then the final stage is now you now get your continental crust again. But now the rocks on those continental crust belong to some orogenic activity, to some orogenic events that happened in stage F to stage H. So some important terminologies, and with that we'll end this video. Some important terminologies. A shield is generally a region of exposed Precambrian crystalline igneous and high-grade metamorphic rocks. They form in tectonically stable areas, and we'll define what tectonically stable means, because there's usually some kind of bar. So wherever you have Precambrian crystalline igneous and high-grade metamorphic rocks exposed on the surface, that area is called a shield. If the area is a large area, so it's not just a small area, but a large area, it's usually called a shield. A platform, on the other hand, is also a continental area. It is underlain by also basement, but it is covered by relatively flat or gently tilted sedimentary rocks. So a region where you have a sedimentary basin where the units are largely flat or gently tilted, beneath which you have basement rocks, that area is called a platform. And then when we look at basement areas, we distinguish between basement areas that are called cratons. Now cratons are old, relatively stable portions of the continental crust. And the bar we use for old and stable is that crust has not been deformed or metamorphosed as a result of an orogeny or continent-continent collision, or collision with some island arc terrain or something in the past 1 billion years. So cratons will include areas where the basement is exposed, so those are the shield areas, and also areas covered by platform sediments, even platform sediments of quaternary ages, of recent ages. So yes, whether it is covered by sediment or not, a craton is basically that the basement is more than 1 billion years old. Orogenic belts, on the other hand, they develop where the continental plate is crumpled and pushed to form mountain ranges as a result of, like I said, continent-continent collision or continent-island arc collision, etc. And it involves a number of geologic processes: metamorphism, crustal thickening, magmatism, and then the whole process, it's collectively called an orogenesis. So I hope that this video will form like a kind of preamble that you should watch before you go into the videos of the lecture slides, because it helps to understand certain concepts that we'll be using a lot when the lectures begin. Thank you.